Here is the question that I ended the previous part of this video lecture with, and let's go through the reasoning. So the first part of the motion is at constant speed, and so the acceleration there should be 0, and that eliminates A and C. In the next part, it's slowing down, and so the acceleration should point opposite to the direction of motion, and so that eliminates D, and the answer must be B. You might be a little worried about these points because you haven't seen how to deal with a reversal of direction. So remember that these 2 points are the same point, and so the velocity just before this is here, and the velocity just after it is here, and we can now do the vector subtraction, and it looks like this, and tells us that the acceleration points back to the left, which is what's in the diagram. Let's just think about what happens when we don't have motion in a straight line. So again, for a race car going around a corner in this top view, we can just take our VF, take our VI, flip it around, add that to VF, and now our delta V points like so. And so we know that our average acceleration through this time period points about this way. So let's now see how this vector subtraction that is involved in calculating an average velocity plays out in a very general situation. So I've made a motion that sort of includes everything, including the kitchen sink. It's got speeding up in a straight line, slowing down in a straight line, constant velocity, going around a corner at constant speed, going around a corner while slowing down, and going around a corner while speeding up. That's all the possibilities. And I've put the acceleration vectors on for the cases that we already know. When it's speeding up in a straight line, the acceleration points in the direction of motion. When it's slowing down in a straight line, the acceleration points opposite to the direction of motion, and constant velocity means 0 acceleration. But let's now see, by carrying out the vector subtractions, how it turns out for the other 3 cases. So let's now use this process of vector subtraction to estimate the acceleration vector at this circled time here. So I'm going to copy those vectors out. Here is my VF, roughly. And here is my VI, roughly. And remember that I need to flip my VI end for end to get negative VI. So I'm going to draw that. And so now I'm going to take my VF and I'm going to add my negative VI to it. And my result points this way. And so notice if I just copy that over, it points inward into the curve, and roughly perpendicular to the direction that the object would be going right at this moment. So now let me do the same process for this moment here when this object is going around a corner while speeding up. And I've already copied out my VF and VI vectors. And remember that what I need to do is flip my VI so that I have negative VI. And now I'm going to add my negative VI to my VF. And so notice that this time, if I copy that up here, that acceleration vector is not perpendicular to the direction of motion. The direction of motion is roughly like this, and so perpendicular to it is roughly like this, and that vector is pointing forward of that. We'll see why in a little while. So now let me finish up by doing this case over here where it's slowing down while turning, and I've copied out my VI and my VF, and I've already made my flipped around negative VI, and I'm going to take my VF and my negative VI and add them. And if I copy that over here, you see that it is not perpendicular or parallel to the motion. The direction perpendicular to the motion would be roughly like this. And so this is pointing into the curve and somewhat back. And again, we'll see why in a little while. But now let's use this idea of decomposing vectors to think about the meaning of accelerations that point at various angles to our velocity vector, because we saw how our acceleration can point in various directions relative to the velocity. So here's some trajectory of an object, and at some time I'm saying it's got the velocity and acceleration vectors shown, where notice that the velocity is tangent to the trajectory as it has to be. We can use a particularly useful decomposition of the acceleration. We can decompose it into a component parallel to the velocity and a component perpendicular to the velocity. And these two components have very specific meaning. Remember that in one dimension, if the acceleration was in the direction of the motion, then the object was speeding up. And if it was opposite the direction of motion, then the object was slowing down. Well, if we only have a parallel component of the acceleration, we're back in that situation. And so we know that if the parallel component of the acceleration is in the same direction as the velocity, then the object must be speeding up. And if it's in the opposite direction as the velocity, then it must be slowing down. What's left over is the perpendicular component of the acceleration. And if that's non-zero, then that means the velocity is changing direction. And so we can look at a case like this, where the acceleration is opposite the direction of the velocity and to the side. And in this case, we would see that this object must be slowing down because the parallel component of the acceleration is opposite the velocity. And the trajectory also must be curving up in this case. Whereas in this case, this object must be speeding up and its trajectory must be curving to the right.